This is Momentum 4 standard, and I'm going to go over one specific example, but the gist of this is that you are going to be creating an if chart that models a collision or an explosion. So the point of Momentum 4 is that you would be able to model a collision or explosion. So I'm going to look at a collision here, but the same could be done if two things, say, started at rest, like two ice skaters, and then they pushed off of each other, and then they have some final velocity, both each in opposite directions. So we're looking right now at a collision. The scenario that I have is I've got this football player, and he's heading in this direction at 5 meters per second. I know his mass is 80 kilograms. And I've also got this defender here in blue, and he's 70 kilograms, and he's running in this direction 2 meters per second. So this is before the collision happens, and then I drew a picture for afterwards. After they tackle each other, or they collide with each other, and I know that when they hit each other, then their final speed is 1.73 meters per second in that direction. I could also figure out the total mass of these players. Total mass, well, that should just be the mass of one plus the mass of the other. So 80 plus 70 is equal to 150 kilograms. Wonderful. So let's start to model this with an if chart. We start with two graphs, or the structure of two graphs, and then label IF. For initial and final, this corresponds with the before scenario. This corresponds with the after scenario. I could write that out. Initial and then final. We have to first consider how many objects we have at play in our collision or explosion. I see two of them. So I'm going to denote this with width of a bar. So check this out. I've got 80 kilograms for this offensive running back, and I'm going to make a bar here for 80 kilograms and label that. I'm also going to make a bar for my 70 kilogram person, but this person is not as heavy as that person, so my bar is going to be representative of that and be a little bit smaller, and I'll label that 70 kg. Cool. Next thing I'm going to do is, on my initial graph, I'm going to say that there's a forward direction and a backward direction. It's very important that you denote the directions, because I have two guys and they're traveling in opposite directions. One's heading forward, the other must be heading backward if I call this direction forward. Okay, so now on the y-axis, on this axis here, I'm going to put in my velocity that I know. Well, look at this. I know my velocity of this offensive running back to be 5 meters per second. So I'm going to go ahead and label that as 5 meters per second. And I can draw this bar. Now this is mass over here. This is velocity over here. Let me label that. Velocity. And I know that mass times velocity is momentum. Remember that from earlier units. Mass times velocity is equal to momentum. So if I do 80 times 5, I get 400. And that's the amount of momentum in this running back that I can label as the area of this bar. 400 kg meter per second. I'm getting that from multiplying length times width, or mass times velocity, same deal. It's the area in this bar. Okay, what about this 70 kilogram fullback? Well, he's heading in the backward direction and he's going 2 meters per second. So it's important that I make the bar shorter. This would be 2 meters per second. If that is 5, this should be about 2, and I'll make my bar something like that. Okay, and then color that in. I'll move the 70 kilogram up here so that we can see it. Okay. Same deal. I'm going to try and figure out the momentum in this bar, or the area in this bar. So I would do 70 times 2, which is 140 kilogram meter per second. But this is below the 0 line, so I know it's negative. Great. The final part to my I side, and then I'm done. I need to find the total momentum. I'm going to say MOM for short. Total momentum. And that can be done by adding up our two values that we've already found. So here we found 400. Down here is negative 140, so I'm going to do plus negative 140, and I can find the total initial momentum. And when I plug that into a calculator, I get 260 kilogram meter per second. This is an important number for us, so I'm going to box that. And I'll explain why in a little bit. Okay, let's move on to the after side. When these guys collide, now they have a total mass of 150, so I need to denote that with a bigger bar. Let's say that is 150 kilograms. I still have the same direction. I still have forward up here and backward down here. Okay, and I know that the velocity is 1.73, so I'm going to make sure that I make this representative. If this is 5, then 1.73 must come down here. And this is 1.73 meters per second, so this is my bar. Check that out. That's my momentum bar. And I could do mass times velocity, or length times width. Notice that's the area of this rectangle. And when I do that in my calculator, 150 times 1.73, I get, what do I get? About 259.5, which is about 260 kilogram meter per second if we round it. Oh my, look at that. This value is the same as that value. The final momentum is the same as the total initial momentum. The total final momentum is the same as the total initial momentum. This is momentum 4. We have modeled a collision, but you should be able to do the same with an explosion. All right. Talk to you guys soon. Goodbye.